Subscribe to the channel so you don't miss out on any of these videos. Space is full of wonders, but some of the most jaw-dropping mysteries are happening in places we can't see with the naked eye, inside the hearts of stars. Imagine this: a gigantic star, one that's been burning for millions of years, suddenly experiences an explosion deep within itself, not on the outside, but in its very core. No fiery eruption visible from Earth, no supernova lighting up the sky, yet this invisible detonation is violent enough to completely change the star's future. This mind-boggling phenomenon is called a helium flash, and it's one of the wildest events in the life of a red giant. What makes this even more fascinating is how silent and hidden it is. It's like a cosmic secret, an explosion that no telescope can see, but one that completely rewrites the rules for how that star behaves from that point onward. If you've ever wondered what happens to stars as they age, buckle up, because the helium flash is the kind of deep space drama that feels almost too incredible to be real. So, what exactly is a helium flash? To understand it, we have to go deep into the science of stars, specifically, how they live, age, and die. Stars, as massive as they are, don't live forever. They're essentially gigantic nuclear furnaces powered by reactions at their cores. These reactions start with hydrogen, the simplest and most abundant element in the universe. Inside a young star, hydrogen atoms fuse together to create helium, releasing enormous amounts of energy in the process. This energy is what keeps the star shining for millions or even billions of years. But eventually, the hydrogen supply starts to run out. When that happens, a star doesn't just give up and fade away, it fights back. It starts fusing helium into even heavier elements like carbon and oxygen. But there's a catch. Fusing helium requires much higher temperatures and pressures than fusing hydrogen. For smaller stars like the Sun, this transition isn't smooth. The core shrinks under its own gravity, growing hotter and denser until conditions are extreme enough to ignite helium fusion in a sudden, explosive burst, the helium flash. The physics of this process is absolutely wild. Picture the star's core as a pressure cooker, with gravity pressing inward and heat building up to unimaginable levels. But there's another layer to this story that makes it even stranger. The core of a red giant is degenerate. That doesn't mean it's immoral or corrupted. It's a physics term that means the core is supported by a weird kind of pressure that doesn't follow the usual rules. Degenerate matter is so dense that atoms are packed together tighter than you'd think possible, and normal temperature increases don't expand it. Instead, as the core heats up, it becomes more unstable, almost like a ticking time bomb. At a certain point, the pressure and temperature in this degenerate core becomes so extreme that helium nuclei slam together with enough force to overcome their natural repulsion. This triggers a runaway reaction, an avalanche of helium fusion that releases an enormous amount of energy in a matter of seconds. But instead of tearing the star apart, the energy is quickly absorbed by the surrounding layers. It's like a massive explosion that no one outside the star can see, but it completely transforms the core's structure. This transformation is crucial. The helium flash essentially resets the star, allowing it to stabilize for a while and enter a new phase of its life. Without this event, the star wouldn't be able to move forward in its evolutionary journey. After the helium flash, the core expands and cools, stopping the runaway reactions. Helium fusion continues, but in a controlled manner, producing carbon and oxygen, the building blocks of life itself. In a way, the helium flash is a star's last big effort to stay alive, creating the elements that will one day form planets, oceans, and even living beings. But why does the helium flash matter to us? For one thing, it helps us understand the life cycle of stars, including our Sun. While the Sun is still billions of years away from this stage, it will eventually become a red giant, swell up to many times its current size, and go through its own helium flash. This event will mark the beginning of the end for the Sun, ultimately leading to its transformation into a white dwarf, a small, dense remnant that will slowly cool and fade over trillions of years. The helium flash is also a key piece of the puzzle when it comes to the chemical evolution of the universe. The heavier elements we see around us, everything from the carbon in your body to the oxygen you breathe, were created in the hearts of stars. The violent nuclear reactions triggered by the helium flash are part of this process, spreading these elements throughout space when the star eventually dies and sheds its outer layers. Without events like the helium flash, the universe would be a much simpler, less interesting place, lacking the diversity of elements needed for life as we know it. What's even more mind-blowing is how scientists study something as hidden as the helium flash. Since the event happens entirely within the star and doesn't produce any light or radiation we can detect, researchers rely on indirect evidence and computer models to understand it. Observing red giants and white dwarfs in various stages of their lives helps piece together the story. These models show that helium flashes are incredibly common in stars of a certain size and composition, but their exact details remain one of the great mysteries of astrophysics. The more we learn about the helium flash, the more questions arise. Why does the reaction proceed differently in stars of different masses? How does the surrounding material absorb the explosion's energy without destroying the star? And could understanding this phenomenon reveal new insights into the ultimate fate of the universe? These are questions that astronomers and physicists are still trying to answer, pushing the boundaries of what we know about stars and their life cycles. It's fascinating to think that such a dramatic, transformative event happens entirely out of sight, hidden within the heart of a star. The helium flash is a reminder of just how mysterious and surprising the universe can be. Even in the most well-studied areas of science, there are still secrets waiting to be uncovered, hidden in the silent explosions and invisible transformations of the cosmos. The helium flash also serves as a cosmic paradox, an explosion so immense that it fundamentally alters the star's internal structure, yet so concealed that no light or shockwave escapes to the outside. This silent but violent event underscores how the most significant changes in the universe often occur in the shadows, beyond what even our most powerful telescopes can observe. Understanding the helium flash is like solving a puzzle with missing pieces, where the clues lie in the aftermath rather than the event itself. The aftermath of the helium flash is nothing short of transformative. After the explosion, the star's degenerate core expands and stabilizes, while the intense heat generated spreads outward. This heat initiates a stable helium fusion process in the core, a phase known as the horizontal branch in stellar evolution. During this stage, the star burns helium into carbon and oxygen in a steady and controlled manner, shining with a newfound stability. This marks a crucial turning point in the star's life cycle, as it temporarily halts its rapid aging and prolongs its existence. But this phase doesn't last forever. As the helium fuel in the core becomes depleted, the star enters its final stages of life. For low to medium mass stars, like our Sun, this means shedding their outer layers to form a planetary nebula, leaving behind a white dwarf, a dense, dim remnant composed mostly of carbon and oxygen. In this way, the helium flash plays a critical role in creating the elements necessary for life and dispersing them into the cosmos, contributing to the cycle of star formation and planetary creation. One of the most intriguing aspects of the helium flash is how it challenges our understanding of extreme physics. The conditions leading up to the event, where temperature and pressure reach unimaginable levels, push the limits of what we know about matter and energy. The degeneracy pressure that supports the core defies intuition, as it operates independently of temperature, unlike normal gases. This unique state of matter is governed by quantum mechanics, specifically the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. This principle creates an exotic environment where the star's core is compressed to the density of a white dwarf long before the star itself reaches its end. As the helium flash ignites, the sudden energy release would normally expand the core violently, but the degenerate nature of the matter resists this expansion. Instead, the energy dissipates into the surrounding layers, heating them and causing the star to adjust its internal structure. This interplay of forces, gravity, pressure, heat, and quantum mechanics, is a delicate dance that scientists are still striving to fully understand. It's a reminder that even the smallest particles in the universe, like electrons and helium nuclei, play a massive role in shaping the cosmos. The study of helium flashes also opens a window into the lives of other stars. While our Sun is destined to experience a helium flash billions of years from now, stars of different masses and compositions undergo similar but distinct processes. For instance, more massive stars don't develop degenerate cores and instead transition smoothly to helium fusion without a flash. Understanding these variations helps astronomers refine their models of stellar evolution, providing insights into the diversity of stars across the galaxy and beyond. One particularly fascinating avenue of research involves the role of helium flashes in binary star systems. In such systems, two stars orbit each other closely enough that material can flow between them, significantly altering their evolutionary paths. When one star in a binary system experiences a helium flash, the energy release can affect its companion, potentially triggering new phases of fusion, or even causing explosive events like novae. These interactions highlight how the lives of stars are interconnected, with one star's helium flash potentially influencing the fate of another. The helium flash also connects to broader questions about the universe's ultimate fate. By studying how stars evolve and distribute elements through processes like the helium flash, scientists gain a better understanding of the chemical enrichment of galaxies over time. The elements forged in these stellar interiors, carbon, oxygen, and eventually heavier elements in more massive stars, are the building blocks of everything from planets to living organisms. Without processes like the helium flash, the universe would remain a barren expanse of hydrogen and helium, devoid of the complexity needed for life. Another layer of intrigue comes from the challenges of observing helium flashes. Since the event itself is invisible, scientists rely on indirect evidence to study it. One method involves observing populations of stars in clusters, where many stars have similar ages and compositions. By analyzing the properties of red giants and their descendants, astronomers can infer details about the helium flash and its effects. Advances in computational astrophysics have also been critical, allowing researchers to simulate these events and explore scenarios that would be impossible to recreate in a laboratory. These simulations have revealed surprising details about the dynamics of helium flashes. For example, the energy released during the flash is equivalent to the detonation of trillions of nuclear bombs, yet it's contained entirely within the star's core. The surrounding layers act as a buffer, absorbing the energy and redistributing it throughout the star. This energy transfer not only stabilizes the star but also causes observable changes in its surface properties, such as luminosity and temperature. These changes provide indirect evidence of the flash, offering astronomers a glimpse into this hidden phenomenon. The mystery of the helium flash is a testament to the complexity and wonder of the universe. It's a reminder that even in the seemingly quiet moments of stellar evolution, there are hidden dramas unfolding, events that shape the cosmos in profound ways. As we continue to study these phenomena, we deepen our understanding of the universe and our place within it. And yet, the helium flash is just one chapter in the larger story of stellar evolution. It's a fleeting moment in a star's life, yet its impact resonates across the cosmos, influencing everything from the formation of new stars to the creation of the elements that make up our world. It's a cosmic explosion that no one sees, but its effects are felt everywhere, a silent yet powerful force shaping the destiny of the universe. The helium flash is not just a single isolated event but part of a grander cycle of cosmic creation and transformation. To understand its broader significance, one must delve into the delicate interplay of forces and reactions within the stellar core that set the stage for this dramatic phenomenon. Before the helium flash ignites, the star's core has already undergone a long and arduous journey. Hydrogen fusion in the core sustained the star during its main sequence phase, producing helium as a byproduct. Over billions of years, the core becomes increasingly dominated by helium, and as hydrogen fusion dwindles, the star begins to evolve into a red giant. The transition from main sequence star to red giant is a pivotal period in stellar evolution. With the depletion of hydrogen in the core, fusion shifts to a shell surrounding the inert helium core. This shell burning releases enormous amounts of energy, causing the outer layers of the star to expand and cool. The result is the characteristic swollen appearance of a red giant, a phase that will eventually culminate in the helium flash. But before this explosion can occur, the helium core must reach conditions of extreme density and temperature, conditions that challenge our understanding of matter itself. The degenerate core at the heart of a red giant is one of the most exotic states of matter found in the universe. Unlike ordinary matter, where pressure and temperature are closely linked, degenerate matter is governed by quantum mechanics. In this state, the electrons are packed so tightly together that their quantum properties create a pressure independent of temperature. This degeneracy pressure is what allows the helium core to resist gravitational collapse, but it also means that as more material is added to the core, its density increases without a corresponding rise in temperature, until a critical tipping point is reached. At this tipping point, the temperature in the core finally becomes high enough to ignite helium fusion. However, because the degenerate core doesn't expand to release pressure like a normal gas, the initial fusion reactions trigger a runaway effect. Within seconds, a massive amount of energy is released, equivalent to the combined output of an entire galaxy. This is the helium flash, a burst of nuclear energy so intense that it reorganizes the star's internal structure. The aftermath of the helium flash is as fascinating as the event itself. The explosion destabilizes the degenerate state of the core, causing it to expand and cool slightly. This expansion relieves the extreme pressures, halting the runaway fusion and allowing the star to settle into a new equilibrium. The core transitions from being dominated by degeneracy pressure to being supported by the heat generated from ongoing helium fusion. This marks the beginning of the horizontal branch phase, a relatively stable period where the star burns helium in its core and hydrogen in a surrounding shell. During the horizontal branch phase, the star takes on new characteristics. Its luminosity and surface temperature stabilize, giving it a distinct place on the Hertzsprung-Russell diagram, a tool astronomers use to classify stars. The changes in the star's properties also have implications for the surrounding interstellar environment. The energy output from the star's fusion processes contributes to the enrichment of the interstellar medium, setting the stage for future generations of star formation. In some cases, the helium flash can have even more dramatic consequences, especially in binary star systems. When one star in a binary system experiences a helium flash, the sudden release of energy can transfer material to its companion star. This transfer can trigger new phases of fusion in the companion, or even lead to explosive phenomena like novae or supernovae. These interactions highlight the interconnected nature of stellar evolution, where the fate of one star can profoundly influence the destiny of another. Despite the advances in our understanding, many mysteries remain about the helium flash. For example, the exact conditions that trigger the flash and the detailed mechanisms of energy transfer within the star are still areas of active research. Observing the aftermath of helium flashes in distant stars and simulating these events using advanced computational models are key to unraveling these mysteries. Each new discovery not only deepens our knowledge of the helium flash but also enhances our understanding of stellar physics as a whole. The study of helium flashes also intersects with broader questions about the universe's chemical evolution. Elements like carbon and oxygen, which are produced during the helium-burning phase, are critical for the development of planets and life. Without the helium flash and the processes it initiates, these elements would remain locked within the cores of stars, never to be released into the cosmos. The helium flash, therefore, is not just an astronomical curiosity but a vital chapter in the story of cosmic creation. As we gaze up at the stars, it's humbling to consider the violent, hidden processes that shape their lives. The helium flash, occurring deep within the core of aging stars, is a reminder of the universe's complexity and the intricate dance of forces that govern it. From the quantum mechanics of degenerate matter to the grand cycles of element creation and dispersal, the helium flash is a microcosm of the dynamic, interconnected universe we inhabit. And yet, the helium flash is just one piece of a much larger puzzle. Its study offers insights into the lives of stars, the nature of matter, and the processes that have shaped the cosmos since its earliest days. As scientists continue to probe the mysteries of the helium flash, they not only illuminate the hidden workings of the universe but also bring us closer to understanding our own origins in the stars. The helium flash is an essential cornerstone in understanding the universe's broader tapestry, serving as a critical mechanism for cosmic recycling and the propagation of life-enabling elements. To grasp its significance fully, we must explore not only its physical mechanics but also its implications for the evolution of galaxies, planetary systems, and even the conditions that gave rise to life on Earth. One of the most intriguing consequences of the helium flash lies in the star's role as a cosmic alchemist. Before this dramatic event, a star primarily fuses hydrogen into helium. This process, while releasing energy, does not produce the heavier elements required for complex chemistry and biology. The ignition of helium fusion in the core marks the first step toward creating carbon and oxygen, two elements vital for organic life. As the helium flash stabilizes the core and initiates this new fusion phase, it sets the stage for these heavier elements to accumulate. When the star eventually sheds its outer layers, either through a slow process like stellar wind or a more violent ejection, the carbon and oxygen produced in its core are dispersed into space. This material enriches the surrounding interstellar medium, seeding future generations of stars and planets with the raw ingredients for life. Every atom of carbon in your body, every molecule of oxygen you breathe, likely originated in the fiery core of a red giant, catalyzed by a helium flash billions of years ago. The role of the helium flash in this chain of creation emphasizes its profound importance. Without this explosive mechanism, low and intermediate mass stars might never produce the carbon and oxygen that underpin the chemistry of life. The flash is a hidden architect of the cosmos, forging the building blocks of everything from the air we breathe to the structures of galaxies. Galactic evolution itself is heavily influenced by the helium flash. In densely populated star clusters, where red giants are abundant, the energy and elements released during and after helium flashes contribute to the chemical diversity of the galaxy. Over billions of years, these processes enrich the galactic environment, enabling the formation of more complex systems, including stars with planetary systems capable of supporting life. In this way, the helium flash is not just a stellar event, it's a galaxy-shaping phenomenon, a contributor to the dynamic, ever-evolving structure of the cosmos. The helium flash also serves as a fascinating testbed for understanding extreme physics. The combination of quantum mechanics, nuclear reactions, and gravitational forces within the core of a red giant creates conditions that push the boundaries of our scientific theories. For instance, the transition from degeneracy pressure to thermal pressure during the helium flash involves processes that are still not fully understood. This interplay between microscopic quantum phenomena and macroscopic stellar behavior is a frontier of modern astrophysics, offering insights that could potentially inform other fields of study, such as particle physics or cosmology. Another aspect of the helium flash that captivates scientists is its role in stellar diversity. Not all stars experience a helium flash in the same way. In stars slightly more massive than the Sun, the core temperatures rise high enough to initiate helium fusion smoothly, without a runaway explosion. These stars bypass the helium flash entirely, demonstrating how small differences in mass can lead to dramatically different evolutionary paths. By studying these variations, astronomers can piece together a more comprehensive picture of how stars evolve, interact, and ultimately influence their surroundings. Binary star systems present yet another layer of complexity. In close binary systems, where one star undergoes a helium flash, the dynamics of mass transfer between the two stars can lead to exotic phenomena. For instance, the material ejected during or after the helium flash might accrete onto the companion star, triggering additional fusion events or altering its evolutionary trajectory. These systems are laboratories for extreme astrophysics, where the interplay of gravity, fusion, and orbital mechanics creates outcomes that challenge our understanding of stellar evolution. While the helium flash is inherently invisible to direct observation, its fingerprints can be seen in the properties of star clusters and individual red giants. Astronomers use tools like spectroscopy and photometry to study the aftermath of helium flashes, analyzing changes in a star's luminosity, temperature, and chemical composition. By comparing these observations to theoretical models, scientists refine their understanding of the helium flash and its role in stellar evolution. This iterative process of observation and modeling is a cornerstone of astrophysics, allowing us to uncover the secrets of phenomena that lie beyond the reach of direct measurement. The implications of the helium flash extend even to the ultimate fate of the universe. As stars evolve and release heavier elements into space, they contribute to the ongoing cycle of star formation and destruction. This cycle influences the long-term trajectory of cosmic evolution, shaping galaxies and determining the availability of resources for future star systems. In this context, the helium flash is a microcosmic event with macrocosmic consequences, a single chapter in a story that spans billions of years and countless stars. Moreover, the study of helium flashes offers a window into the broader question of how matter behaves under extreme conditions. The degenerate cores of red giants, where electrons are packed to quantum limits, provide natural laboratories for studying states of matter that are otherwise inaccessible. These insights have applications beyond astronomy, informing fields as diverse as materials science and nuclear engineering. The helium flash, in this sense, is not just an astrophysical phenomenon but a key to unlocking new knowledge across scientific disciplines. Despite the progress made in understanding the helium flash, many questions remain. For example, how do variations in a star's initial composition affect the timing and intensity of the flash? What role do magnetic fields play in the dynamics of the event? And how might future observations, such as those from next-generation space telescopes, refine our models? These unanswered questions underscore the complexity of the helium flash and its central role in the puzzle of stellar evolution. The helium flash encapsulates the duality of the universe, its quiet, concealed origins juxtaposed with its far-reaching, transformative effects. Though hidden from view, this explosion reshapes the stars that host it and profoundly influences the cosmos at large. It is a testament to the interconnectedness of the universe, where even the most isolated events ripple outward, touching countless lives and systems in ways we are only beginning to understand. As our understanding of the helium flash deepens, we uncover not just the story of stars but the story of ourselves. The elements forged in the heart of red giants, catalyzed by helium flashes, are the same elements that form our bodies, fuel our technology, and sustain our ecosystems. In studying this hidden explosion, we are exploring our own origins, tracing the threads of existence back to their stellar roots. The helium flash is an intricate piece in the tapestry of cosmic phenomena, tying together the life cycle of stars, the formation of elements, and the evolution of galaxies. It exemplifies how the most extraordinary processes in the universe often occur far from human perception, yet have profound implications for the very fabric of existence. As we delve deeper, the interconnectedness of the helium flash with other celestial phenomena becomes even more evident. For instance, the elements formed in the aftermath of the helium flash, carbon and oxygen, are not just essential for life on Earth but also act as catalysts for the birth of new stars and planets. These elements, scattered into the interstellar medium during the later stages of a star's life, contribute to the formation of molecular clouds. These clouds, rich in heavy elements, are the cradles of new stellar systems. Without the helium flash and its role in producing these elements, the universe would be a much less diverse and vibrant place. Interestingly, the helium flash serves as a bridge between the quiet, stable phase of a star's life and its eventual demise. In low-mass stars like our Sun, the helium flash sets the stage for a transformation into a red giant that sheds its outer layers. This expulsion forms a planetary nebula, leaving behind a dense core, a white dwarf. These white dwarfs are fascinating objects, composed mostly of carbon and oxygen created during and after the helium flash. They slowly cool over billions of years, becoming cosmic relics that silently tell the story of their earlier explosive transitions. In intermediate mass stars, the helium flash can indirectly lead to the creation of neutron stars or black holes. While these outcomes require a more massive progenitor, the processes initiated during the helium fusion phase lay the groundwork for the star's eventual collapse. The heavier elements synthesized during helium burning, such as neon and magnesium, contribute to the core's evolution, influencing whether the star undergoes a supernova or quietly transitions to its final state. The helium flash also offers a rare glimpse into the principles of quantum mechanics at play on a stellar scale. The phenomenon of electron degeneracy pressure, which temporarily halts the collapse of the core, is a direct result of quantum mechanical principles. This same pressure is responsible for the stability of white dwarfs and contributes to the Chandrasekhar limit, the maximum mass a white dwarf can attain before collapsing further into a neutron star or black hole. The helium flash, therefore, is not just a standalone event but a crucial link in understanding the broader physics of compact objects and stellar remnants. Furthermore, the helium flash holds implications for the study of stellar populations and galaxies. By analyzing the properties of red giants that have undergone helium flashes, astronomers can infer the age, composition, and evolutionary history of star clusters. This information is invaluable for constructing models of galactic evolution, providing clues about how galaxies like the Milky Way have developed over billions of years. The helium flash acts as a marker in the timeline of stellar evolution, a signpost that helps us piece together the larger narrative of the cosmos. The phenomenon also highlights the fine balance between stability and chaos in the universe. The degeneracy pressure that builds up before the helium flash represents a delicate equilibrium, one that can be disrupted by even the smallest changes in temperature or density. This precarious balance is a reminder of how finely tuned the processes of the universe are, with tiny variations leading to vastly different outcomes. Such considerations inspire broader philosophical questions about the nature of existence and the forces that govern it. Advancements in observational technology have begun to shed more light on the helium flash and its aftermath. Space telescopes equipped with advanced spectrographs can analyze the chemical composition of red giants and their surrounding nebulae, offering indirect evidence of the elements produced during helium burning. These observations not only validate theoretical models but also provide new data points for refining our understanding of stellar physics. Theoretical models, too, have evolved to incorporate the complexities of the helium flash. Advanced simulations can now replicate the conditions leading up to and following the flash, providing insights into its dynamics and consequences. These models are essential for understanding phenomena that are otherwise inaccessible, given the impossibility of observing the helium flash directly. They also serve as a testing ground for broader theories of astrophysics, helping scientists refine their understanding of nuclear fusion, stellar structure, and energy transport. Despite these advancements, many mysteries surrounding the helium flash remain. For instance, the precise mechanisms that dictate the intensity and duration of the flash are not fully understood. Variations in a star's metallicity, the abundance of elements heavier than hydrogen and helium, can significantly affect its evolution, including the nature of the helium flash. Unraveling these nuances requires a combination of observational data, theoretical modeling, and experimental research, underscoring the interdisciplinary nature of astrophysics. The helium flash also serves as a reminder of the interconnectedness of scientific discovery. Understanding this stellar event requires insights from multiple fields, including quantum mechanics, thermodynamics, and nuclear physics. Each piece of the puzzle contributes to a more comprehensive picture, illustrating how the pursuit of knowledge is a collaborative effort that spans disciplines and generations. In contemplating the helium flash, we are reminded of the universe's duality, its immense scale and its intricate details. This hidden explosion, occurring deep within the cores of aging stars, is a microcosm of the cosmic processes that shape the universe. It is a testament to the power of science to uncover the secrets of the cosmos, revealing the extraordinary and the seemingly ordinary. As we look to the future, the study of the helium flash will undoubtedly continue to evolve. New technologies, such as next-generation space telescopes and advanced computational models, will provide deeper insights into this enigmatic phenomenon. These advancements will not only enhance our understanding of the helium flash but also shed light on the broader processes that govern the universe, from the birth of stars to the emergence of life itself. The helium flash, though hidden from view, is a profound reminder of the universe's capacity for transformation and renewal. It is a fleeting moment in the life of a star, yet its impact resonates across the cosmos, shaping galaxies, creating elements, and ultimately enabling the conditions for life. In studying this hidden explosion, we uncover not just the story of stars but the story of the universe, and our place within it. The helium flash represents one of the many extraordinary yet hidden processes that make the universe what it is. To truly understand its significance, we must recognize the roles it plays not just in the life of a single star but in the grander cosmic cycle of birth, death, and rebirth. Every helium flash is a critical moment in the timeline of a star, yet its effects ripple outward to influence galaxies, interstellar clouds, and even the conditions that make life possible on planets like Earth. To grasp the full picture, let's revisit the dramatic physics that lead up to a helium flash. Inside the core of a red giant star, the temperature and pressure steadily rise as gravitational contraction compresses the core into a highly dense state. As we discussed earlier, degeneracy pressure takes over, halting the collapse temporarily. This quantum mechanical effect is fascinating because it has no counterpart in the macroscopic world we experience daily. The pressure arises not from thermal motion but from the fundamental principles of quantum physics, specifically, the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. This degeneracy pressure stabilizes the core, but it also creates a ticking time bomb. As helium accumulates and fuses under the growing temperature, energy is released in a runaway reaction because the degeneracy pressure doesn't allow the core to expand and cool like a typical gas would. This sets the stage for the helium flash, a dramatic, nearly instantaneous event where an immense amount of energy is released in a fraction of a second. It's worth noting that the amount of energy released during a helium flash rivals that of a supernova explosion, albeit confined to the core of the star and invisible to outside observers. When the helium flash occurs, it not only marks the start of helium fusion into carbon and oxygen but also has profound structural effects on the star. The energy released during the flash is enough to break the degeneracy pressure, allowing the core to expand and cool. This expansion stabilizes the star and initiates a new phase of life in the helium burning stage. The star's outer layers adjust accordingly, often leading to changes in its luminosity and size. For red giants, this can mean a temporary pause in their outward swelling, as the newfound stability in the core counteracts the gravitational forces at play. The significance of the helium flash extends beyond the individual star. The products of helium fusion, primarily carbon and oxygen, are critical building blocks of the universe. These elements are later released into space during the star's final phases, enriching the interstellar medium. Without this process, the cosmos would lack the heavy elements needed to form planets, organic molecules, and life itself. The helium flash, therefore, is a key player in the cosmic alchemy that transforms simple elements like hydrogen and helium into the rich diversity of matter we see around us. From an observational standpoint, the helium flash is nearly impossible to detect directly. However, its effects are written across the light and spectra of stars. Astronomers use advanced tools to study the chemical compositions of stars and their remnants, piecing together the story of the helium flash and its aftermath. For example, globular clusters, ancient collections of stars bound together by gravity, provide valuable laboratories for studying the effects of helium flashes. In these clusters, stars evolve predictably due to their similar ages and compositions, allowing scientists to test theories about stellar evolution and the role of the helium flash. One of the most intriguing aspects of the helium flash is its variability depending on the star's initial mass and composition. In stars with higher metallicity, the presence of heavier elements affects the opacity of the stellar material, which in turn influences the temperature and density conditions in the core. These variations can alter the intensity and duration of the helium flash, providing a rich field of study for astrophysicists. By comparing models of stars with different metallicities, researchers can gain insights into the history of element formation in the universe. Moreover, the helium flash plays a pivotal role in shaping the evolutionary paths of binary star systems. In some cases, the material ejected during or after a helium flash can be transferred to a companion star, altering its mass and evolution. This mass transfer can lead to exotic phenomena such as novae or even the formation of double degenerate systems, where two white dwarfs orbit each other in close proximity. These systems are thought to be progenitors of certain types of supernovae, making the helium flash an indirect but vital contributor to some of the universe's most spectacular events. The study of helium flashes also intersects with the search for life beyond Earth. The elements produced during and after helium flashes, particularly carbon, are foundational to organic chemistry. By understanding the processes that create and distribute these elements, scientists can better estimate where and how life-sustaining environments might arise in the galaxy. In this way, the helium flash is not just a stellar phenomenon but a piece of the broader puzzle of astrobiology. As we continue to explore the cosmos, new technologies promise to deepen our understanding of the helium flash. Upcoming space missions equipped with ultra-sensitive spectrometers may be able to detect indirect signatures of helium flashes in distant galaxies, offering a window into the evolution of stars in different cosmic environments. Additionally, advances in computational astrophysics will allow for more detailed simulations of the helium flash, shedding light on aspects of the phenomenon that remain poorly understood. The helium flash is a testament to the complexity and beauty of the universe, a hidden explosion that shapes the destinies of stars and galaxies alike. It is a reminder that even the most dramatic events can occur in silence, far from the reach of human senses, yet leave an indelible mark on the cosmos. By studying this remarkable phenomenon, we not only deepen our understanding of the stars but also our appreciation for the intricate web of processes that make the universe what it is. The journey to uncover the mysteries of the helium flash is far from over. Each discovery brings new questions, driving us to explore further and think deeper. In the end, the helium flash is more than just a moment in the life of a star. It is a symbol of the relentless cycle of creation and transformation that defines the universe itself. The helium flash is not just a single chapter in the life of a star, it is part of an intricate tapestry of stellar evolution. To truly appreciate its role, we need to delve deeper into the physics, chemistry, and cosmic consequences that it entails. The event itself is fleeting, occurring over mere seconds to minutes, but its impact is enduring, influencing the star's structure, its eventual demise, and even the environments that emerge in its wake. As we've discussed, the core dynamics leading to a helium flash are dominated by quantum mechanical principles. One of the most fascinating aspects of this process is the interplay between degeneracy pressure and thermal pressure. In most systems, heat and temperature act as stabilizing forces. For example, when you heat up a balloon, the air expands, relieving some of the pressure. However, in the degenerate core of a red giant, this intuitive relationship breaks down. The core's pressure is largely independent of its temperature because of the degeneracy pressure, creating a unique environment where runaway fusion can occur without a proportional increase in core expansion. This runaway reaction releases an enormous amount of energy in a very short time frame. Some estimates suggest that during the peak of the helium flash, the core may release energy at a rate equivalent to the total luminosity of the Milky Way galaxy. However, this energy is rapidly absorbed and redistributed within the star, ensuring that the event remains hidden from external observation. This internalized nature of the helium flash is both a blessing and a curse for astrophysicists. On one hand, it makes direct observation impossible. On the other, it forces scientists to rely on clever indirect methods and detailed simulations to understand the phenomenon. One of the key outcomes of the helium flash is the initiation of the triple alpha process, a fusion reaction that converts helium into carbon and oxygen. This process occurs in two main stages. First, two helium nuclei, alpha particles, collide to form beryllium-8, an unstable isotope that typically decays almost instantly. However, in the extreme conditions of a stellar core, a third helium nucleus can collide with beryllium-8 before it decays, forming a stable carbon-12 nucleus. The efficiency of this process is highly temperature-dependent, which is why the helium flash, with its sudden spike in core temperature, is so effective at jump-starting it. The production of carbon and oxygen during this phase is not just a biochemical curiosity, it's the foundation of all life as we know it. Carbon is the backbone of organic molecules, while oxygen is essential for processes like respiration and water formation. Without the helium flash and the subsequent triple alpha process, the universe would be a vastly different place, likely devoid of the complex chemistry needed for life. The aftermath of the helium flash also has profound effects on the star's outer layers. As the core expands and stabilizes, the energy released from helium fusion provides an outward pressure that balances gravitational forces. This newfound equilibrium often leads to changes in the star's luminosity and size. For some stars, this stabilization marks the beginning of a relatively peaceful helium-burning phase, during which they shine steadily for millions of years. For others, particularly those in binary systems, the helium flash can trigger dramatic mass loss events, enriching the surrounding space with heavy elements. These ejected materials play a crucial role in the cosmic recycling process. When stars shed their outer layers, they release not only helium but also heavier elements like carbon and oxygen. These materials mix with interstellar gas clouds, seeding the formation of new stars and planets. Over time, this process leads to the gradual enrichment of the universe with heavier elements, a phenomenon known as cosmic chemical evolution. The helium flash, while invisible to the naked eye, is one of the pivotal steps in this grand cycle, linking the life and death of stars to the birth of new worlds. Understanding the helium flash also helps astronomers refine their models of stellar populations. In globular clusters, for example, the helium flash plays a crucial role in shaping the horizontal branch, a phase of stellar evolution that follows the red giant phase. By studying the horizontal branch and comparing it to theoretical models, scientists can infer the age, composition, and history of these ancient stellar groups. This, in turn, provides valuable clues about the early history of our galaxy and the conditions under which it formed. Another intriguing aspect of the helium flash is its role in the evolution of low-mass stars. For stars below a certain mass threshold, approximately 2.5 times the mass of the Sun, the helium flash is a defining moment. These stars lack the mass needed to ignite helium fusion gradually, making the flash an inevitable consequence of their evolutionary path. In contrast, higher-mass stars can ignite helium more smoothly, bypassing the explosive nature of the helium flash. This distinction highlights the diverse outcomes of stellar evolution and underscores the importance of mass as a determinant of a star's fate. The study of helium flashes also intersects with the search for exotic astrophysical phenomena. For instance, some theories suggest that under certain conditions, helium flashes could lead to the formation of unusual compact objects, such as helium-rich white dwarfs, or even helium-burning stars. These hypothetical objects, while rare, could provide new insights into the behavior of matter under extreme conditions and the limits of nuclear fusion. As we continue to refine our understanding of the helium flash, new questions inevitably arise. What role do magnetic fields play in shaping the dynamics of helium flashes? How do variations in a star's rotation rate or initial chemical composition affect the intensity and timing of the flash? These and other questions drive ongoing research, pushing the boundaries of our knowledge and deepening our appreciation for the complexity of stellar evolution. The helium flash is more than just a dramatic event in the life of a star, it's a window into the underlying mechanisms that govern the universe. By studying this phenomenon, we not only learn about the physics of stars but also uncover the processes that have shaped the cosmos over billions of years. The helium flash is a reminder that even the most fleeting events can have profound and lasting consequences, influencing everything from the formation of planets to the emergence of life itself. The helium flash's significance extends beyond the immediate stellar reactions it triggers. Its cascading effects ripple through the cosmos, influencing star clusters, galactic evolution, and even the potential for life in the universe. To fully grasp its implications, we must continue unpacking its role in the broader astrophysical context and the intricate mechanics driving its occurrence. One of the most striking aspects of the helium flash is how it defies the intuitive behavior of matter under extreme conditions. In most systems, as temperature increases, the pressure also rises, leading to predictable expansion. However, in the degenerate core of a red giant, where electrons are tightly packed and follow quantum rules, this relationship is inverted. Pressure remains nearly constant regardless of temperature increases, allowing the runaway nuclear reaction to escalate unchecked. This unique environment underscores the profound interplay between classical and quantum physics in shaping the cosmos. The burst of energy during the helium flash is transformative, resetting the star's core dynamics. Before the flash, the core is dominated by helium ash left behind from earlier hydrogen fusion in the surrounding shell. This helium is compressed into an extremely dense state, with temperatures climbing steadily but not high enough to ignite fusion. Once the critical temperature threshold is crossed, often around 100 million Kelvin, the triple alpha process begins with ferocity, converting helium into carbon at an explosive rate. This conversion is not merely a chemical reaction but a nuclear one, producing vast quantities of energy. The energy release stabilizes the core, breaking the degeneracy and allowing it to expand. This expansion cools the core slightly, slowing the helium fusion to a more sustainable pace. In essence, the helium flash marks the transition from a chaotic, unstable phase to a more orderly helium-burning phase, akin to the calm after a storm. The aftermath of the helium flash is equally compelling. The core's expansion reduces the pressure on the surrounding hydrogen-burning shell, which in turn diminishes the energy output from the star's outer layers. For observers, this can manifest as a temporary decrease in luminosity, followed by a more stable brightness as the star settles into its new equilibrium. This phase of stability, known as the horizontal branch in the Hertzsprung-Russell diagram, can last millions to billions of years, depending on the star's mass and composition. This stable period is not just an astronomical curiosity, it's a vital stage in the life cycle of elements. During this time, the triple alpha process continues to produce carbon and oxygen, laying the groundwork for the formation of planets, moons, and ultimately, the building blocks of life. Without the helium flash and its role in igniting helium fusion, the universe would lack the diversity of elements needed to create complex structures. As stars undergoing the helium flash age further, they often shed their outer layers, creating stunning planetary nebulae. These nebulae are rich in heavy elements forged during the star's life, including carbon, oxygen, and traces of other nuclei formed in secondary fusion reactions. The material ejected into space becomes part of the interstellar medium, enriching the cosmic environment for future generations of stars and planetary systems. In this way, the helium flash contributes directly to the cycle of stellar birth, death, and rebirth. The helium flash also provides a fascinating lens for studying stellar populations in clusters. In globular clusters, for example, stars often evolve through similar stages due to their shared age and composition. By observing the horizontal branch and related phenomena, astronomers can infer critical details about the cluster's age, metallicity, and history. This makes the helium flash not just an event in individual stars but a key piece of the puzzle in understanding the broader history of our galaxy. Interestingly, the helium flash might also have implications for the search for extraterrestrial life. The elements produced during this phase are essential for the chemistry of life as we know it. Carbon forms the backbone of organic molecules, while oxygen is crucial for water, one of life's fundamental solvents. The helium flash, therefore, plays a hidden but vital role in shaping environments where life could potentially arise. Advances in computational astrophysics have allowed researchers to simulate the helium flash in unprecedented detail. These simulations reveal subtle nuances in how the event unfolds, such as the role of turbulence in mixing elements within the core or the influence of rotation on the flash's intensity. Such models are invaluable, providing insights that are impossible to glean from direct observation alone. Beyond individual stars, the helium flash sheds light on broader cosmic phenomena, such as the formation of white dwarfs. After exhausting their helium fuel, low to intermediate mass stars expel their outer layers and leave behind a dense core. This core, composed primarily of carbon and oxygen produced during the helium burning phase, becomes a white dwarf. The properties of these remnants, such as their mass and composition, are directly influenced by the dynamics of the helium flash. Moreover, the helium flash offers a fascinating perspective on the limits of stellar evolution. For stars below a certain mass threshold, the flash is an unavoidable milestone. But for more massive stars, helium fusion ignites more gradually, bypassing the explosive nature of the flash. This dichotomy highlights the delicate balance of forces and conditions that govern the lives of stars and adds another layer of complexity to our understanding of the universe. Even the challenges of studying the helium flash are illuminating. Its hidden nature forces scientists to innovate, developing new techniques and technologies to probe the interiors of stars. Instruments like neutrino detectors and space-based observatories are pushing the boundaries of what we can observe, bringing us closer to a comprehensive understanding of stellar evolution. In many ways, the helium flash is a microcosm of the universe itself, a fleeting, explosive event that leaves an indelible mark on its surroundings. It is a reminder that the cosmos is a dynamic, ever-changing place, where even the smallest details can have profound implications. By studying the helium flash, we not only uncover the secrets of stars but also gain a deeper appreciation for the interconnectedness of all things, from the tiniest atoms to the vastness of galaxies. The story of the helium flash is far from over. As our tools and techniques improve, new discoveries will undoubtedly emerge, deepening our understanding and sparking fresh questions. In the grand tapestry of the cosmos, the helium flash is a single, brilliant thread, one that illuminates the intricate patterns of creation, destruction, and renewal that define our universe. As we continue to delve into the incredible mechanics of the helium flash, it becomes clear that this event is not just a momentary explosion, but a transformative phase in the life cycle of stars that has lasting effects on the universe. The more we study this phenomenon, the more we realize how interconnected the different stages of stellar evolution are, and how the helium flash plays a pivotal role in both the individual life of a star and the broader cosmic landscape. At its core, the helium flash is a prime example of how stars can exhibit behaviors that defy expectations. Stars are not just burning balls of gas, but intricate systems governed by complex physics. The quantum effects that occur in the dense cores of red giants lead to an environment where traditional laws of thermodynamics and pressure balance no longer apply in the same way. This is a feature that is most evident during the helium flash. In the immediate aftermath of the flash, the core experiences a dramatic transformation. The sudden release of energy leads to a rapid expansion, which, as mentioned earlier, temporarily stabilizes the star's internal structure. But the process doesn't stop there. The outer layers of the star, still burning hydrogen, continue their fusion in the shell surrounding the newly stabilized core. The intensity of this hydrogen fusion process often increases as a result of the helium flash, causing the star to shine brighter and hotter than before. The star has now entered a new phase, often referred to as the horizontal branch phase, where it burns helium steadily for millions to billions of years. This steady burning of helium is an essential phase for many stars, particularly those in the range of mass that allows them to transition from the unstable state before the helium flash to the relative stability afterward. But the processes that occur during the helium flash have much broader consequences, influencing not only the star's own future but also its impact on the galaxy around it. For example, consider the material that is ejected from a star after its helium flash. In the later stages of stellar evolution, particularly in red giants, these outer layers are expelled into space, creating a nebula of gas and dust. These nebulae are often rich in elements like carbon and oxygen, which were created during the helium burning phase. This material is not wasted, it becomes part of the interstellar medium, where it may one day contribute to the formation of new stars, planets, and even life forms. In this sense, the helium flash plays a direct role in the continuous cycle of star birth and death that shapes the universe. The nature of these planetary nebulae is a subject of great interest in modern astrophysics. They are not just beautiful phenomena, as their colorful displays captivate observers, but they are also the remnants of a star's life cycle, carrying with them the story of the star's evolution and its final transformation. As the star sheds its outer layers, the remaining core becomes a white dwarf, composed primarily of carbon and oxygen. Over time, this white dwarf will cool and fade, but it remains an important part of the universe's ongoing evolutionary process. The helium flash is also essential to understanding the broader dynamics of stellar populations, particularly in star clusters. In globular clusters, where stars are formed around the same time and share a similar chemical composition, the helium flash acts as a kind of cosmic marker, helping astronomers determine the age and history of these clusters. By studying the stars on the horizontal branch and their evolution after the helium flash, scientists can better understand the processes that govern star formation and the life cycle of stellar systems. One of the key challenges in studying the helium flash is that it is such a short-lived and highly localized event. Unlike supernovae or other large-scale explosions that release vast amounts of energy and can be observed from vast distances, the helium flash is a much more subtle phenomenon. Its effects on the star are profound, but they often go unnoticed by astronomers who are focused on more dramatic events. Yet, as we improve our observational technology and refine our understanding of stellar evolution, we are beginning to uncover more about the helium flash's role in the grand scheme of the universe. For example, advancements in spectroscopy and the study of stellar oscillations, or astroseismology, are providing new insights into the structure of stars and the way they evolve over time. By examining the vibrations of a star, scientists can gain detailed information about its internal structure, including the processes that occur during the helium flash. These tools allow us to observe stars in greater detail than ever before, shedding light on the intricacies of stellar behavior that were once beyond our reach. Another fascinating aspect of the helium flash is the way it interacts with the stellar environment. The energy released during the flash does not just affect the star itself, it can have a ripple effect on the surrounding matter in space. For example, the increased luminosity and temperature of the star after the flash can influence the surrounding interstellar gas and dust, potentially triggering new star formation or affecting the evolution of nearby celestial objects. In this sense, the helium flash can be seen as a catalyst for change in the broader cosmic environment. Moreover, the helium flash also has implications for the fate of stars in binary or multiple star systems. In such systems, where two or more stars orbit each other, the interactions between the stars can influence their evolution in profound ways. A red giant undergoing a helium flash in a binary system may transfer mass to its companion star, altering both stars' evolutionary paths. This can lead to the formation of exotic objects such as white dwarfs, neutron stars, or even black holes, depending on the mass and characteristics of the stars involved. Looking ahead, the study of the helium flash and its consequences will continue to be a vital area of research in the field of astrophysics. As our telescopes and computational models improve, we will gain an even deeper understanding of how stars evolve and interact with their environments. This will not only enhance our knowledge of the stars themselves but also provide new insights into the fundamental forces that govern the universe. In the future, the role of the helium flash in the formation of elements and the potential for life elsewhere in the universe may become clearer. The carbon and oxygen produced during the helium flash are essential building blocks for life, and understanding the precise conditions under which they are created could offer important clues about the origins of life on Earth and the possibility of life elsewhere in the cosmos. The helium flash, in many ways, represents both the destructive and creative forces of the universe. It marks the end of a star's life as a hydrogen-burning entity, but it also ushers in a new era of helium fusion that produces the elements necessary for the formation of planets and life. In this way, the helium flash is a reminder of the intricate balance between creation and destruction, a balance that shapes not only the lives of individual stars but the entire cosmos itself. As we look to the future, it is clear that the helium flash, with its sudden and dramatic onset, will continue to fascinate and inspire astronomers and astrophysicists alike. It serves as a testament to the incredible complexity of the universe and our ever-deepening understanding of the forces that shape it. The helium flash, despite being one of the more elusive and enigmatic events in stellar evolution, holds profound implications that extend beyond the star in question. As we continue to explore this phenomenon, we uncover its far-reaching effects on galactic evolution, the formation of new stars, and even the chemical composition of the universe. It's essential to understand that the helium flash isn't an isolated event. Rather, it is one part of a larger sequence of events in the life of a star, particularly those that fall into the red giant category. These stars are often the progenitors of some of the most important chemical elements that populate the universe, contributing significantly to the material that forms planets, moons, and possibly life itself. The helium flash occurs at a pivotal moment in the star's life cycle, often after it has exhausted its hydrogen fuel in the core and is left to burn helium. This dramatic event marks the transition from a star's hydrogen fusing stage to its helium fusing stage, which can last for billions of years, giving rise to even more massive changes in the star's structure and energy output. However, one of the most fascinating aspects of the helium flash is how it reflects the delicate balance between gravity, pressure, and temperature that governs every stage of stellar evolution. As a red giant nears the end of its hydrogen-burning phase, the core begins to contract under the weight of its own gravity. This contraction increases the core's temperature dramatically, allowing helium to begin fusing into heavier elements. The helium flash occurs when the pressure inside the core becomes so great that the core's helium ignites in a runaway nuclear reaction, causing a sudden release of energy. This burst of energy is extremely powerful, yet short-lived. The intensity of the explosion is enough to drastically alter the internal structure of the star, momentarily halting its core contraction. However, the outward force of the explosion doesn't dissipate, as the star's outer layers continue to exert pressure inward, keeping the core stable in a newly found equilibrium. After this brief period of instability, the core becomes more stable, and the star can now burn helium for an extended period. What makes the helium flash so compelling is the unique conditions required for it to occur. Unlike the fusion of lighter elements like hydrogen, which happens gradually over the course of a star's life, the fusion of helium requires extreme pressures and temperatures. In the dense core of a red giant, helium nuclei fuse together to form heavier elements like carbon and oxygen, but only after reaching a critical threshold of temperature and pressure. This fusion process, which begins with a sudden burst of energy, sets the stage for the star's future development. The changes that happen in a star after the helium flash are striking. For example, the helium flash causes the star to expand significantly, becoming a much more luminous and larger red giant. This expansion happens due to the increase in temperature, which causes the outer layers of the star to puff up. The star's outer envelope cools down as it expands, turning it into a much cooler, but much brighter, object in the sky. While the helium flash doesn't dramatically alter the size of the star in a physical sense, it fundamentally changes how the star shines and how it interacts with its surrounding environment. Interestingly, stars that undergo a helium flash are not isolated objects. In many cases, they are part of binary or multiple star systems, where their interactions with nearby companions can have profound effects on their evolution. In these systems, one star may transfer material to another, enriching the companion with elements like carbon and oxygen, produced by the helium flash. This material may eventually be ejected into space, contributing to the interstellar medium from which new stars will form. These binary interactions also affect the final stages of stellar evolution, leading to the formation of exotic objects such as white dwarfs, neutron stars, and even black holes. The study of the helium flash also opens doors to understanding the broader structure of galaxies and how stars contribute to the cosmic cycle. In star clusters, for example, the helium flash can help astronomers estimate the age and composition of the stars within the cluster. By studying the stars that have recently undergone the flash, scientists can learn more about the conditions that led to their formation and evolution. The helium flash serves as a cosmic timestamp, allowing us to better understand the timing of events in a star's life and its eventual fate. One of the key scientific questions that arises from the study of the helium flash concerns the long-term fate of stars that undergo this event. The process of helium fusion, once ignited, can continue for millions to billions of years, eventually leading to the creation of even heavier elements. These stars, after they have burned through their helium fuel, will eventually enter their final stages of evolution, shedding their outer layers and leaving behind a dense core that becomes a white dwarf. Over time, this white dwarf will cool and fade, but it will remain a part of the cosmic landscape for billions of years. Additionally, the helium flash has implications for the formation of elements in the universe. The carbon and oxygen produced during the flash are crucial for the creation of planets, moons, and even life. These elements, scattered by the stellar winds and planetary nebulae ejected by the star, enrich the interstellar medium, making it possible for new stars and planets to form with the building blocks necessary for life as we know it. This process is integral to the ongoing cycle of star formation and destruction, creating the very materials that allow life to flourish. The helium flash also provides a valuable laboratory for understanding extreme physics. In a star's core, the conditions are so intense that normal physical laws seem to bend and stretch. For example, the quantum effects that occur in the core of a star during the helium flash lead to changes in how particles interact, allowing for processes like the sudden ignition of helium fusion. This can offer insights into areas of physics that are not easily accessible on Earth, giving us a better understanding of the fundamental forces that govern the universe. Moreover, the helium flash serves as a reminder of the finite nature of stars. While they burn for billions of years, eventually, even the most massive stars will run out of fuel. The helium flash marks a critical turning point in this process, one that leads stars to their final stages of evolution. And yet, from the ashes of these dying stars, new stars, planets, and even life can emerge, perpetuating the endless cycle of cosmic birth and death. In a way, the helium flash is both a violent outburst and a sign of regeneration. It's a brief but powerful moment in the lifespan of a star, but it has far-reaching effects on the structure of the star and the universe around it. The burst of energy that occurs during the flash plays a significant role in the formation of new stars and elements, contributing to the ongoing evolution of galaxies, star systems, and even the potential for life. As astronomers continue to observe stars and refine their models of stellar evolution, the helium flash will remain a key focus of study. Its effects are felt across the universe, from the birth of new stars to the enrichment of the interstellar medium. Each helium flash is a cosmic event, a dramatic and transformative process that shapes the future of the star and the galaxy it resides in. By examining these events, we not only learn about the stars themselves but also about the fundamental forces and processes that govern the universe. The helium flash, in all its complexity, is one of the many awe-inspiring phenomena that make up the rich tapestry of the cosmos. As we continue to explore the ramifications of the helium flash, it's crucial to examine the broader implications this event has for the galaxy and even the entire universe. While the helium flash is a short-lived event in the star's life cycle, it is far from insignificant. The explosive release of energy during this period doesn't just alter the star's structure and its inner workings. It affects the very fabric of the galaxy in which it resides, as well as the composition of the interstellar medium. One of the more fascinating aspects of stellar evolution is how stars like red giants, after undergoing a helium flash, contribute to the chemistry of their environment. During their later stages, these stars shed large amounts of their mass, which includes elements like carbon, oxygen, nitrogen, and other heavier elements produced during the flash. This is often ejected into space as a stellar wind or as part of a planetary nebula. These materials then become part of the interstellar medium, an essential building block for the formation of future stars, planets, and potentially life itself. It's a process that reflects the cyclical nature of the universe, where the death of one generation of stars paves the way for the birth of the next. The contribution of these elements has an essential impact on the chemical makeup of the galaxy. Over successive generations of stars, the interstellar medium becomes progressively enriched with heavier elements. This process is known as stellar nucleosynthesis, and it leads to the creation of the complex elements found in planets and, in a broader sense, in life itself. The helium flash plays a pivotal role in this process, contributing to the cosmic recycling that fuels star formation, planetary development, and even life. Without these elements, the universe as we know it would be a barren place, devoid of the conditions required for life. In addition to enriching the interstellar medium, the helium flash plays an important role in the overall evolution of galaxies. As stars undergo this dramatic event, they release energy and material into the surrounding space, triggering new waves of star formation in regions that were previously devoid of activity. The expelled gases and heavy elements provide the necessary raw materials for new stars to form, and these stars, in turn, contribute to the ongoing dynamism of the galaxy. This interplay between the life cycle of stars and the broader galaxy is crucial for understanding how galaxies evolve over time. A galaxy's stellar population is constantly changing and evolving, and the helium flash is one of the key events that helps to drive this transformation. While the helium flash is crucial for stellar and galactic evolution, it also provides valuable insights into the fundamental forces that govern the universe. As mentioned earlier, the extreme conditions within a star's core during a helium flash provide a laboratory for testing our understanding of physics in environments that cannot be recreated on Earth. The fusion of helium and the subsequent formation of heavier elements happen under conditions of incredibly high temperature and pressure, conditions that push the boundaries of what we know about nuclear physics and quantum mechanics. The behavior of matter in such extreme conditions can offer clues to some of the universe's most profound mysteries. For example, understanding how nuclear reactions occur during a helium flash can shed light on the nature of stellar interiors and the dynamics of nuclear fusion. By studying the isotopes and byproducts of these reactions, scientists can learn more about how matter behaves under intense pressure and temperature, potentially offering insights into phenomena like the interior of neutron stars, black holes, and the conditions of the early universe. In some ways, the helium flash is a natural experiment on the immense power of the fundamental forces that govern the universe. As helium nuclei fuse into carbon and oxygen in a star's core, the force of the resulting explosion serves as a reminder of the tremendous energy locked within matter. The sudden release of energy during the flash alters the structure of the star, causing it to expand and cool, which in turn affects its radiation output and the way it interacts with its environment. These dramatic changes allow scientists to study how stars transition between different phases of their life cycles, offering clues about the broader processes of stellar evolution. The study of helium flashes is also essential for understanding the future of our own Sunday. While the Sun is not yet at the red giant phase, it will eventually enter this stage as it exhausts its hydrogen fuel in its core. When this happens, it will start to fuse helium in its core, potentially leading to a helium flash. Understanding the mechanics behind this event and its consequences is key for predicting what will happen to our solar system as the Sun evolves. When our Sun undergoes its helium flash, it will likely experience a dramatic expansion, possibly engulfing the inner planets, including Earth. While this event will mark the end of the Sun's habitability, it will also lead to the formation of new elements in its core, enriching the surrounding space with the materials needed for the next generation of stars and planets. It's a sobering reminder of the transient nature of the stars, and by extension, the Earth. Stars live, die, and are reborn in an endless cycle, with each generation leaving behind the materials that will contribute to the next. As our understanding of the helium flash and stellar evolution grows, we are able to refine our models of stellar life cycles and our predictions about the fate of stars in different environments. Observations from space telescopes and ground-based observatories are continually providing new data about the ages and compositions of stars, which help astronomers refine their models of how stars evolve and what happens during key moments like the helium flash. However, despite all the progress we've made in understanding the helium flash, there are still many mysteries to be solved. For instance, we still don't fully understand the precise conditions under which the helium flash occurs, nor the exact mechanisms by which the flash can trigger further fusion reactions in the star's core. Additionally, there's much to learn about how stars interact with their environments in the aftermath of a helium flash, particularly in terms of how they affect nearby stars, planets, and the surrounding interstellar medium. The helium flash may be a momentary event in the lifespan of a star, but its consequences are far-reaching. By studying this dramatic explosion in red giants, astronomers gain valuable insights not only into the lives of stars but also into the processes that shape the universe itself. From the formation of new elements to the ongoing evolution of galaxies, the helium flash is an event that underpins the very structure of the cosmos. The helium flash is a fascinating and awe-inspiring phenomenon, an explosive reminder of the delicate balance that governs the life and death of stars. As stars age and evolve, the helium flash serves as a crucial step in their transformation, one that influences everything from the composition of the galaxy to the formation of life-sustaining elements. By continuing to study these events, scientists are piecing together a better understanding of the universe's most fundamental processes, and we, in turn, are left with a profound appreciation for the complexity and beauty of the cosmos. As we continue to examine the role of helium flashes in stellar evolution, it becomes clear just how pivotal these moments are in shaping the trajectory of not only individual stars, but also the vast galactic systems in which they reside. While we often view the life of a star as a relatively steady progression from birth to death, events like the helium flash serve as significant turning points, moments of profound change that reverberate throughout a star's future and its surrounding environment. What's fascinating about these stars, particularly the red giants that undergo a helium flash, is the dramatic contrast between their early stages of life and the chaos they face as they evolve. When stars first form, they shine with relatively stable and predictable luminosity, fueled by the fusion of hydrogen into helium in their cores. But as they deplete their hydrogen reserves, their cores begin to contract while their outer layers expand and cool, transforming the star into a red giant. This is where the helium flash comes in, taking a star that has been evolving slowly over millions of years and forcing it into a rapid and often violent transformation. To understand the aftermath of the helium flash, we need to consider what happens inside the star after the fusion of helium begins in earnest. The star experiences a massive and sudden increase in temperature and pressure in its core. This reaction leads to an extraordinary burst of energy, and the core of the star undergoes rapid expansion. This sudden expansion causes the star to cool down momentarily, but in the long term, it stabilizes at a much higher luminosity than before. The surrounding outer layers of the star are ejected into space in the process known as the planetary nebula phase, leaving behind the dense, hot core that has been altered by the flash. The impact on the star's outer layers is equally striking. As the core undergoes this sudden burst of fusion, the outer layers of the star expand massively. This expansion is not uniform, and the outer layers may experience significant instability, causing the star to pulsate or shed material into space. The loss of this material can have long-term effects on the star's evolution, as it carries away essential elements that would otherwise remain in the star's structure. However, the elements lost in the outer layers are not wasted. As they drift through space, they become part of the interstellar medium, contributing to the formation of new stars, planets, and other cosmic bodies. One of the most profound effects of the helium flash is the way it accelerates the formation of heavier elements within the star. Before the helium flash, stars primarily fuse hydrogen and helium in their cores. However, the intense conditions that arise during the flash make it possible for heavier elements to form. This process, which occurs in the cores of red giants, is known as helium shell flashes, and it occurs after the initial helium flash. The helium shell flashes create even more complex and heavier elements, such as carbon, oxygen, and neon. These elements are essential to life as we know it because they serve as the building blocks of planets, life, and the very structure of the universe. Another interesting aspect of the helium flash is how it directly affects the future of the star itself. After the flash, the star enters a phase of stability known as the horizontal branch. Here, the star will undergo a series of fusion processes that involve the fusion of helium into carbon and oxygen, effectively stabilizing the star for a period of time. Depending on the mass of the star, this phase can last millions of years, during which the star will continue to shine brightly. However, once the helium fuel in the core runs out, the star will undergo further stages of evolution, possibly becoming a red supergiant if it's massive enough, or collapsing into a white dwarf if it's less massive. These post-flash phases represent a final push towards the end of the star's life, and in some cases, the end is marked by an explosive death. Stars that are sufficiently massive may undergo a supernova explosion after burning through all their fuel, leaving behind a neutron star or black hole. For less massive stars, however, the end is more peaceful, marked by the gradual fading of the white dwarf into a cold, dark remnant. While these processes are markedly different, they all stem from the same series of dramatic transformations initiated by the helium flash. The impacts of the helium flash are not limited to the stars themselves. When stars undergo such explosive events, the energy released can have far-reaching consequences for the surrounding space. The release of energy and matter in the form of a planetary nebula or stellar wind can interact with nearby gas and dust, triggering new rounds of star formation. This interplay between star death and new birth is an ongoing cycle that shapes the evolution of galaxies. In essence, stars, through their births and deaths, act as both the creators and destroyers of the very fabric of the universe. Furthermore, the helium flash also holds implications for our understanding of the universe's larger-scale structure. While the individual consequences of a helium flash may seem confined to the star and its immediate surroundings, the cumulative effect of many such events over the course of cosmic history has contributed to the ongoing evolution of galaxies. The material expelled by red giants in their final stages of life is rich in heavy elements, contributing to the metal content of galaxies. This process, known as galactic enrichment, is critical for the formation of planets, especially Earth-like planets that could harbor life. Without this enrichment, the universe would be a much more sterile place, devoid of the elements necessary for the development of complex chemistry. As astronomers continue to refine their models of stellar evolution and collect data from distant stars, the understanding of events like the helium flash becomes more precise. The technology at our disposal, including advanced space telescopes like Hubble and the James Webb Space Telescope, allows us to peer deeper into the lives of distant stars and uncover the mysteries of their evolution. For example, observing a star in the throes of a helium flash, or analyzing the remnants of stars that have gone through the process, provides valuable insights into how these events unfold in different environments. This knowledge not only enhances our understanding of stellar life cycles but also helps us predict the future of our Sun and the eventual fate of our solar system. At the same time, researchers are working to understand how the helium flash relates to other stellar phenomena. For example, in some cases, the flash might cause instability in the outer layers of the star, triggering a series of massive pulsations. These pulsations are not only significant in their own right, as they affect the star's structure and energy output, but they also serve as a way for astronomers to study the internal structure of the star. By observing the way a star pulsates, scientists can infer key details about its internal composition, such as the density, temperature, and pressure of the layers inside. In the broader context, the helium flash is just one piece of the larger puzzle of stellar evolution. Understanding how stars progress from one phase to the next, how they transition from the main sequence to red giants, undergo helium fusion, and ultimately reach their final stages, offers crucial insights into the life cycle of the universe itself. In this sense, studying helium flashes is not just about understanding the stars in our own neighborhood. It's about grasping the fundamental processes that have shaped, and continue to shape, the cosmos. The helium flash is an awe-inspiring event that marks a significant chapter in the lives of stars. It serves as a reminder of the vast and dynamic nature of the universe, where even the death throes of stars contribute to the ongoing evolution of galaxies, star systems, and the elements that make up everything we know. While the helium flash may be brief in the life of a star, its impact is lasting, contributing to the creation of the elements, the formation of new stars, and the ongoing cycle of cosmic creation and destruction. The helium flash continues to be a fascinating area of study because it represents a pivotal moment in the life of a star, one that can set the stage for the star's subsequent evolution and the entire future of its surrounding environment. As we explore deeper into these events, it becomes apparent that the helium flash is far from a simple, isolated phenomenon. Its effects ripple outward through space, influencing not only the stars themselves but also the galaxy they reside in. And this has profound implications for the broader universe, creating an interconnected system where stars, planets, and galaxies are bound together by the forces of physics, chemistry, and gravity. The core of a star undergoing a helium flash is a high-pressure, high-temperature environment, where the elements are constantly in motion, colliding, and undergoing nuclear reactions. Before the flash, the core of a red giant is primarily composed of helium, which is a byproduct of the hydrogen fusion that occurred in earlier stages of the star's life. Over time, as the helium accumulates in the core, the conditions become ripe for nuclear fusion to occur. This is what sparks the event known as the helium flash. The process is incredibly rapid, creating intense bursts of energy that result in a dramatic alteration of the star's structure and the dynamics within it. In some stars, the helium flash is so powerful that it temporarily causes the star's core to expand significantly. This expansion creates a temporary cooling effect, causing the star's outer layers to contract, leading to an observable decrease in luminosity. However, this cooling phase is short-lived, as the balance between gravity and the outward pressure from the fusion reactions is eventually restored. After this brief period, the star settles into a new state, often called the horizontal branch, during which it can sustain fusion of helium and heavier elements for a long period. This phase is typically much more stable than the red giant phase that preceded it, marking the start of a new era in the star's life. However, this newfound stability doesn't last forever. Eventually, the helium in the core begins to deplete, and the star faces another round of instability. For low-mass stars, this could result in a transition into the asymptotic giant branch, AGB, phase, during which the star enters a cycle of helium shell flashes. These shell flashes are a series of smaller, less intense events that repeat over the course of millions of years, driving further changes in the star's outer layers. During this phase, the star may shed significant amounts of mass, and its outer layers can expand even more dramatically. The helium flash doesn't just change the star in physical terms, it also alters the chemical composition of the star's interior. As helium fuses into carbon and oxygen, the core becomes richer in these heavier elements. This process not only fuels the star's continued existence for a time, but also contributes to the overall enrichment of the interstellar medium. When the star sheds its outer layers or dies in a supernova, it disperses these elements throughout space, providing the raw materials for future generations of stars and planetary systems. In this way, the helium flash and its consequences are an integral part of the cosmic cycle of star birth, life, death, and rebirth. One of the most intriguing aspects of the helium flash is how it links the life cycles of stars to the broader evolution of galaxies. The energy and material released during a helium flash affect the surrounding environment in profound ways. As the outer layers of the star expand and are expelled into space, they interact with the surrounding gas and dust, potentially triggering new rounds of star formation. This process is known as feedback, and it plays a significant role in the ongoing evolution of galaxies. In some cases, the material expelled from stars during the red giant phase, including those that have undergone helium flashes, can contribute to the formation of new stars. These new stars, in turn, may undergo their own transformations, including further helium flashes, perpetuating the cycle. Moreover, the effects of a helium flash are not always predictable. While some stars might settle into a more stable phase after the event, others may experience further instability, and the star could eventually explode in a supernova. The fate of a star depends largely on its mass, as more massive stars will continue to evolve in ways that smaller stars will not. For example, a star with a mass greater than around 8 solar masses will end its life in a supernova explosion, while a lower mass star will eventually become a white dwarf. The diversity of outcomes following a helium flash speaks to the complexity of stellar evolution. In fact, some of the most fundamental aspects of a star's later life are directly influenced by how it handles the transition from hydrogen fusion to helium fusion. If a star has enough mass and internal pressure, the helium flash will have relatively little effect on its overall fate, as the star may simply continue on to burn even heavier elements. On the other hand, for a star with less mass, the helium flash can mark the end of a stable, long-lived life cycle, with the star eventually shrinking into a white dwarf and fading away over billions of years. Another compelling factor in understanding helium flashes is the role of mass loss in stellar evolution. As stars lose mass during the later stages of their lives, including during the helium flash phase, they contribute to the cosmic cycle of star formation and destruction. Mass loss can occur through processes such as stellar winds, which are enhanced by the energy generated during helium fusion. These stellar winds push material away from the star, including heavy elements that have been synthesized in the core. The expelled material can become part of the interstellar medium, eventually giving rise to new stars, planets, and even life. Interestingly, the release of mass in the form of a planetary nebula can also have an impact on the surrounding stellar population. For instance, As a star loses mass and its outer layers expand, it may influence the orbits of nearby stars or even trigger the collapse of nearby molecular clouds. This feedback mechanism is a key part of how galaxies evolve and grow, as stars that die can help birth new stars in the same galactic neighborhoods. As we continue to explore the lasting effects of helium flashes on stellar populations, we gain new insights into the intricate processes that govern the universe. We begin to see that stars are not just isolated objects, but part of a vast, interconnected network of cosmic events. Each star is a thread in a larger tapestry, with each life cycle contributing to the overall structure and evolution of galaxies, stars, and even the elements that make up life itself. And it's all set into motion by events like the helium flash, moments of destruction and creation that shape the very fabric of the cosmos. This realization highlights the importance of continuing to study the life cycles of stars. Through advancements in telescope technology and computational models, astronomers are uncovering more details about how stars evolve, how helium flashes occur, and how these moments of transformation influence the broader universe. As we peer deeper into the stars and their histories, we gain a clearer picture of how our own sun will one day undergo similar transformations, eventually entering its red giant phase and eventually releasing its outer layers into the vastness of space. The helium flash reminds us that, in the grand scheme of things, the universe is in a constant state of flux. Stars are born, evolve, and die, and each of these moments contributes to the larger story of the cosmos. Whether it's the creation of heavy elements that allow for life, or the birth of new stars that will continue the cycle, helium flashes are a key component in the ongoing evolution of our universe. A reminder that even in the death of a star, new life and new possibilities are always on the horizon. As we continue to delve into the mechanics of the helium flash and its aftermath, we begin to realize that these events are not only critical in the context of stellar life cycles, but also provide insight into the larger processes of cosmic evolution. The interplay between stellar death and the birth of new stars and planetary systems is one of the most fascinating aspects of astrophysics. The helium flash, in its explosive nature, acts as a catalyst, ushering in new forms of energy and matter that fuel the universe's ever-expanding diversity. What's particularly intriguing about the helium flash is its role in the larger framework of stellar nucleosynthesis, the process by which elements are formed in the cores of stars. Before the flash, stars primarily fuse hydrogen into helium through nuclear fusion. Once the hydrogen runs out, the core contracts under gravity, causing the temperature and pressure to rise. This, in turn, allows the fusion of helium into heavier elements like carbon and oxygen. These elements, once produced in the core, have far-reaching consequences. Not only do they alter the composition of the star itself, but they are also released into the universe when the star sheds its outer layers, enriching the interstellar medium and creating a fertile ground for the formation of new stars and planetary systems. But the helium flash is more than just a dramatic increase in fusion rates. It represents a point at which a star undergoes significant internal changes that dramatically alter its outward appearance and behavior. For stars that go through this phase, the structure of the star itself shifts. In the immediate aftermath of a helium flash, the core is typically left in a state that allows it to continue its evolution. The outer layers of the star will often expand greatly, cooling and turning red as they enter the red giant phase. In many cases, this phase is followed by further helium shelf flashes or even a complete shedding of the outer layers of the star. This marks the star's final journey in its life cycle, a process that may eventually lead to the formation of a white dwarf. The helium flash can also significantly impact the star's future rate of energy production. The rapid fusion of helium in the core releases a tremendous amount of energy, but the manner in which that energy is redistributed throughout the star is far from simple. In some cases, the helium flash may result in the establishment of a new balance between gravitational collapse and the outward pressure from fusion. This delicate balance is what determines the star's longevity. For more massive stars, the situation is more complex. These stars will continue to fuse heavier elements, eventually progressing to the fusion of carbon and oxygen in the core. The continuous progression of fusion reactions can lead to increasingly complex and energetic processes, each contributing to the eventual demise of the star in a supernova explosion. Interestingly, the helium flash and the subsequent phases of stellar evolution provide us with one of the keys to understanding the life cycle of stars like our own Sun. As our Sun ages, it will eventually transition into a red giant, where it will undergo similar transformations. While our Sun is not massive enough to undergo a helium flash as dramatic as those in more massive stars, the general principles remain the same. The core will begin to contract as hydrogen runs out, leading to increased temperatures and pressures. The outer layers will expand, and the Sun will enter a phase where it swells up to many times its current size, eventually shedding its outer layers in the form of a planetary nebula. The fate of the Sun will ultimately result in the formation of a white dwarf, an incredibly dense remnant of the original star. The implications of these processes go beyond just the star in question. They also affect the planets and other objects that orbit the star. As a star expands into the red giant phase, its outer layers can engulf nearby planets, heating them to extreme temperatures or even causing their complete destruction. In the case of our own solar system, the Sun's eventual transformation into a red giant will likely lead to the evaporation of Earth and the other inner planets. However, this process is far in the future, and we still have billions of years before the Sun reaches this stage. Furthermore, these events provide a deeper understanding of how planetary systems evolve over time. As stars shed their outer layers, they not only release heavy elements but also change the conditions of their surrounding environments. These newly enriched regions may serve as the birthplaces for new planetary systems, much like how the death of a star paves the way for new stars to form from the surrounding gas and dust. The materials released in the aftermath of a helium flash, elements like carbon, nitrogen, oxygen, and even heavier elements like iron, become the building blocks for future planets and stars. The more we learn about helium flashes and the broader mechanisms of stellar evolution, the clearer it becomes that the universe is in a constant state of flux. Stars are not static objects, but dynamic, ever-changing systems whose fates are shaped by the processes of nuclear fusion, gravitational collapse, and the complex interplay of forces within their cores. Each stage in a star's life, from its birth in a nebula to its death in a supernova or as a white dwarf, is intimately connected to the surrounding universe. The energy and elements released during these processes reverberate throughout space, enriching the cosmos and setting the stage for the next generation of stars and planetary systems. As we study these incredible phenomena, we are continually reminded of the cyclical nature of the universe. What begins in the cores of stars as simple elements like hydrogen and helium eventually gives rise to the elements that form planets, life, and everything we know. The helium flash, with all its explosive energy, plays a pivotal role in this cosmic cycle, transforming stars, enriching the interstellar medium, and paving the way for new life and new stars to take their place in the vast expanse of space. In essence, the helium flash is a symbol of both destruction and creation. It marks a pivotal moment in the life of a star, one that can lead to a period of stability or send the star into further transformation. But in the broader scope of the universe, it is just one step in the ongoing cycle of birth, death, and rebirth. Through these dramatic events, the universe continues to evolve, creating new stars, planets, and possibilities. The helium flash is not just an isolated event in the life of a star. It is a part of a much larger story of cosmic evolution that stretches across billions of years, shaping the future of the universe in profound and lasting ways. As we continue to explore the aftermath of the helium flash, we must recognize the far-reaching consequences that stem from the sudden and dramatic changes in a star's internal structure. The internal dynamics, which had been relatively stable during the star's earlier phases, are now drastically altered. The intense energy released by the helium flash causes the core to briefly expand before cooling down again. This expansion can trigger a temporary increase in the star's luminosity, which can be observed as a sudden brightening in the sky. The immediate effects on the star's outer layers are also significant. As the core undergoes rapid changes, the outer envelope may expand greatly, causing the star to swell into the red giant phase. This expansion is often accompanied by a decrease in surface temperature, giving the star its distinctive red appearance. Despite the cooler outer layers, the core becomes extremely hot and dense, providing the necessary conditions for helium fusion and further nuclear reactions. It is during this stage that stars begin to burn heavier elements, and the fusion processes are pushed to their limits. For stars of lower mass, such as our Sun, the helium flash marks the beginning of the final phases of stellar evolution. These stars will experience multiple helium flashes, which help sustain their luminosity for a time, but eventually, they will exhaust their nuclear fuel. The core will continue to contract, while the outer layers will continue to expand. Over time, the core's temperature will increase to the point where carbon and oxygen begin to fuse, marking a new phase in the star's life cycle. However, these stars will not undergo the violent supernova explosions seen in more massive stars. Instead, they will shed their outer layers gently, leaving behind a hot, dense core known as a white dwarf. In contrast, more massive stars, those several times heavier than the Sun, experience a more tumultuous fate. After undergoing helium flashes, the star's core will continue to contract and heat up, eventually reaching temperatures and pressures sufficient for the fusion of heavier elements like carbon and oxygen. This process continues until the core reaches the necessary conditions for the fusion of iron. The creation of iron in a star's core signals the end of its fusion processes. Iron cannot be fused to release energy, and without the outward pressure from fusion, gravity takes over. The result is a catastrophic collapse, leading to a supernova explosion. While the mass of the star determines its ultimate fate, the helium flash serves as a turning point in all cases. It is the moment when a star's internal processes become unstable, leading to an inevitable transformation. As these stars evolve, they provide critical insights into the life cycle of stars and the complex mechanisms that govern stellar nucleosynthesis. The heavy elements produced during the helium flash, as well as subsequent stages of fusion, play an essential role in the cosmic recycling process, enriching the interstellar medium with elements that will later form new stars and planets. Moreover, the helium flash is part of a broader narrative about the universe's ongoing transformation. The energy released during these stellar events contributes to the expansion of the universe. This energy propagates outward, influencing the surrounding interstellar medium and shaping the dynamics of galaxies. It's not just the star itself that is affected by the helium flash, but also the very environment in which it exists. The interstellar medium, which is composed of gas and dust, will absorb some of this energy and material. Over time, the enriched medium becomes a nursery for the birth of new stars, planets, and even life. These processes underscore the interconnectedness of the universe. Each star, no matter how far away, is a fundamental part of the cosmic web. The matter and energy that stars create, especially during explosive events like the helium flash, are passed on to the next generation of stars and planets. The heavy elements forged in the cores of stars are the same elements that form the Earth, our own Sun, and even ourselves. The helium flash and the processes that follow are not merely part of the story of a single star. They are part of a larger cycle that governs the very fabric of the universe. The more we learn about these stellar processes, the more we realize just how little we know. While much has been uncovered about the mechanisms at work during the helium flash, there are still many mysteries surrounding its exact causes and effects. What triggers the sudden onset of helium fusion in the core? How exactly does the energy from the helium flash transfer to the outer layers, triggering expansion? And what are the long-term consequences of these events on the surrounding space? These are questions that astronomers and astrophysicists continue to grapple with as they observe stars undergoing their final transformations. In recent years, advancements in technology have allowed us to study these events in more detail than ever before. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope will enable astronomers to observe stellar evolution with unprecedented precision. These observations will shed light on the complex processes that govern the life cycles of stars, offering deeper insight into the mechanisms at play during the helium flash and beyond. By studying stars in various stages of evolution, scientists hope to build a more complete picture of how stars live, die, and give rise to the next generation of cosmic bodies. As we look toward the future, it is clear that the helium flash will continue to be a focal point of stellar research. This incredible event, though brief in duration, plays a crucial role in shaping the universe. It serves as a reminder of the dynamism of the cosmos, where even the most stable of objects, like stars, are in a constant state of change. Through our exploration of the helium flash, we gain a deeper understanding of the processes that fuel the universe and the cycles of birth, death, and rebirth that govern the life of stars. The helium flash is not just a scientific curiosity, it is a key to understanding the universe's history and its future. By studying these events, we are not only learning about the stars themselves but also uncovering the very principles that shape the cosmos. From the elements in the air we breathe to the very fabric of space-time itself, the legacy of these stellar explosions extends far beyond the stars in which they occur. It is a story that spans the eons and touches everything in the universe, including us. As we continue to explore the long-term effects and broader significance of the helium flash in the context of stellar evolution, it's essential to examine the role of this dramatic event in the larger life cycle of a star. While the flash itself may only last a few moments in cosmic terms, the ripple effects it causes span millions or even billions of years. Understanding these far-reaching consequences helps to provide a clearer picture of the evolution of stars, the creation of the elements, and the role of these phenomena in the broader cosmic processes. One of the immediate effects of the helium flash is that it marks the transition from the red giant phase to the next stages in stellar evolution. For stars of low to medium mass, the helium flash can trigger a period of stability known as the horizontal branch phase. During this phase, the star's core is primarily composed of helium, and it burns helium through fusion reactions. The outer layers of the star expand once again, though not as significantly as during the red giant phase, and the star stabilizes for a while before eventually running out of fuel. For stars of higher mass, the helium flash leads to the fusion of heavier elements in the core, starting with carbon and oxygen. The fusion of these heavier elements increases the star's temperature and pressure, triggering a cycle of more fusion events. As the star continues to burn through heavier and heavier elements, it goes through a series of stages that lead to the creation of a variety of elements in the star's core, such as neon, magnesium, and silicon. Ultimately, this cycle will culminate in the creation of iron, a stable element that cannot be fused to release energy. Once the star's core is dominated by iron, the star can no longer generate the energy needed to counteract the crushing force of gravity. This sets the stage for a dramatic end to the star's life, whether in a supernova explosion or another form of stellar death, depending on its mass. For many stars, the energy generated by the helium flash leads to the formation of a planetary nebula. This is a cloud of gas and dust that is expelled from the star's outer layers during its final stages. As the star sheds its outer envelope, it leaves behind a dense core that becomes a white dwarf. The white dwarf is a remnant of the star's former self, a tiny, hot, and extremely dense object that no longer undergoes fusion reactions. Over time, the white dwarf will cool and fade, eventually becoming a cold, dark object known as a black dwarf, although this process takes longer than the current age of the universe. The fate of a star depends on its mass, with more massive stars meeting a much more dramatic end. Instead of becoming a white dwarf, these stars will undergo a supernova explosion. This violent event releases an immense amount of energy, causing the star to collapse in on itself before expanding outward in a massive shockwave. This shockwave blows off the star's outer layers, enriching the surrounding interstellar medium with elements like oxygen, carbon, and nitrogen, key ingredients for future stars and planets. The remnants of the star may collapse into a neutron star or, if the star is massive enough, a black hole. The helium flash, although brief in comparison to the entire lifespan of a star, is a critical moment in this process. It represents the start of a series of nuclear reactions that shape the composition of the star and its eventual fate. In many ways, it is the key to understanding the cycle of matter in the universe. The elements created during the fusion process in the cores of stars, particularly those that occur after the helium flash, are the building blocks for life as we know it. Carbon, oxygen, and nitrogen, elements essential to life, are forged in the hearts of stars and spread throughout the galaxy during stellar death. This cycle of birth, death, and rebirth is what allows the universe to maintain a constant exchange of energy and matter, fostering the conditions necessary for the formation of planets and life. As we study stars undergoing helium flashes, astronomers also look at the chemical composition of these stars and their surrounding environments. By examining the spectrum of light emitted by stars in various stages of evolution, scientists can determine the abundance of various elements present in the star and the interstellar medium. This provides clues about the star's age, mass, and history. Additionally, by studying how stars evolve, researchers can learn about the formation and evolution of galaxies themselves, as stars are the building blocks of galaxies. In the grand scheme of cosmic events, the helium flash is just one piece of a much larger puzzle. However, its role is pivotal, as it represents the point at which a star's energy production shifts dramatically, and its subsequent actions can lead to a variety of outcomes that shape the universe around it. The discovery and understanding of the helium flash have opened up new avenues for research, allowing scientists to explore the depths of stellar evolution with greater precision and insight. In fact, there are still many unanswered questions regarding the helium flash and the role it plays in stellar evolution. For example, what exactly triggers the helium flash in a star? How do stars manage to overcome the internal pressure from their outer layers to initiate such a dramatic event? These questions are at the forefront of modern astrophysics, and researchers continue to seek answers by conducting simulations, gathering observational data, and studying stars at various stages of their life cycles. The upcoming advancements in space observation technology hold great promise for further revealing the secrets of stellar evolution. Instruments like the James Webb Space Telescope, which is capable of observing stars and galaxies in infrared wavelengths, will allow astronomers to peer into the hearts of distant stars in greater detail than ever before. These observations will provide a more comprehensive understanding of how helium flashes occur in different types of stars, and what their broader implications are for stellar life cycles, element creation, and the evolution of galaxies. As we continue to push the boundaries of our knowledge, we are also gaining a deeper appreciation for the intricate, interconnected processes that govern the cosmos. Every star, no matter how distant, contributes to the ongoing transformation of the universe. From the helium flash and red giants to the formation of new stars and planets, these cosmic events are the lifeblood of the universe, ensuring that it remains dynamic and ever-changing. Understanding the helium flash is not just about understanding stars, it's about understanding the very forces that shape the universe as a whole. The helium flash reminds us that even the most stable and enduring stars are subject to change. Their fates are sealed by the intricate dance of nuclear reactions occurring within their cores, and this dance is governed by the fundamental forces of physics. The study of these forces provides us with not only answers to questions about stars but also insights into the origins of the universe itself. It's a story that spans billions of years and touches every corner of the cosmos, and as we continue to learn about it, we get closer to unraveling the mysteries of the universe. As we continue our exploration of the helium flash and its broader cosmic implications, it's important to delve deeper into the specifics of what happens within the core of a star during this event. The mechanics of stellar fusion are both complex and awe-inspiring, providing a rich field of study for astrophysicists. Understanding these mechanics not only helps to explain the helium flash but also illuminates the life cycle of stars as a whole, shedding light on the formation of elements that make up the universe we know today. At the heart of the helium flash is a process known as degeneracy pressure. When a star's core contracts as it burns through hydrogen, it reaches a point where the temperature and pressure are high enough to start fusing helium into carbon and oxygen. However, before this can happen efficiently, the core becomes extremely dense due to the exhaustion of hydrogen in the core and the corresponding contraction of the outer layers. This density leads to a state known as electron degeneracy pressure, which halts further collapse of the core, even though the temperature is still rising. This pressure caused by the electrons in the core is crucial to the onset of the helium flash. Unlike a normal gas, where particles can move freely and exert pressure, in a degenerate gas, the particles are confined by quantum mechanical effects. This results in the core being able to reach much higher temperatures before nuclear fusion can begin in earnest. This sudden leap in temperature triggers a rapid and uncontrollable fusion of helium, creating enormous amounts of energy in a very short amount of time. The result is an explosive flash of energy that can temporarily change the structure and appearance of the star. However, this is just the beginning. The helium flash not only marks a transition in the star's core but also has profound effects on its outer layers. As the core of the star stabilizes and begins to burn helium, the outer layers expand once again, often resulting in the star becoming a red giant once more. This expansion is a consequence of the energy produced by helium fusion, which radiates outward and pushes against the gravitational forces of the star. The star's outer envelope may grow immensely, sometimes to the size of a small solar system, before it stabilizes again. But there's another twist in the story of the helium flash. As stars of different masses undergo this process, the helium flash can take on various forms. In stars with lower masses, the helium flash is often a relatively smooth process, and the star will continue on its journey toward becoming a white dwarf. For stars with greater mass, however, the flash may not be so gentle. The increased pressure and temperature in the core of the star can lead to the fusion of heavier elements, and the core may become unstable once more. In such stars, the core may oscillate, leading to a complex series of events that will eventually end in a dramatic explosion, a supernova. For stars of all sizes, the helium flash represents a key moment in the overall process of stellar evolution. For lower mass stars, it paves the way for a slow but steady descent into the white dwarf stage, where the star's remaining fuel is exhausted and its outer layers dissipate into space. The remnants of the star, now composed mostly of carbon and oxygen, are extremely dense and compact, containing a significant portion of the star's original mass. These white dwarfs gradually cool over billions of years, becoming colder and fainter, until they eventually become black dwarfs, cold, dark remnants of once vibrant stars. In contrast, more massive stars undergo a much more explosive end. After the helium flash and subsequent fusion processes, these stars may experience multiple stages of fusion, culminating in the creation of iron in their cores. Once iron builds up to a critical mass, the star can no longer support itself against gravitational collapse, and the result is a catastrophic supernova. This violent explosion releases an enormous amount of energy, and during this event, many of the heavier elements that make up our planet and everything on it are forged. Elements like gold, platinum, and uranium are produced in the heart of these stellar explosions, enriching the surrounding galaxy with heavy elements that can later be incorporated into new stars, planets, and even life itself. But even after a star's death, the helium flash and its aftermath continue to shape the universe. The death of stars through supernovae or white dwarf formation serves as a critical part of the cosmic cycle. The shockwaves produced by supernovae send matter and energy into the surrounding interstellar medium, triggering the formation of new stars and planets. This process is crucial to the ongoing development of galaxies and the replenishment of the cosmic material necessary for the formation of life. Without the death of stars, the universe would be a barren place, devoid of the elements needed for life to exist. As we look toward the future, our understanding of the helium flash and its role in stellar evolution is bound to deepen. Advancements in technology, particularly in the field of observational astronomy, will allow scientists to observe stars undergoing helium flashes with unprecedented detail. Instruments like the James Webb Space Telescope, which can peer deeper into space and observe stars at various stages of their evolution, will help us understand not only how stars evolve but also how the process of stellar death impacts the larger structure of the universe. Moreover, our understanding of these processes could have profound implications for our understanding of the origins of life. The elements that make up our world, carbon, oxygen, nitrogen, and more, are formed in the cores of stars, and the helium flash plays a pivotal role in this process. These elements, forged in the heat of stars, are the building blocks of everything in the universe, including life. As we continue to study stars and their evolution, we gain a deeper appreciation for the interconnectedness of the cosmos, and the role that each star plays in the larger narrative of the universe's development. The helium flash, then, is much more than just an event that occurs in the life of a star. It is a key moment in the ongoing dance of matter and energy that shapes the cosmos. It is a testament to the dynamic, ever-changing nature of the universe, and it reminds us that even in the death of a star, there is rebirth. The materials created in the core of stars are scattered throughout the galaxy, enriching the interstellar medium and creating the conditions for new stars, planets, and life to emerge. The study of the helium flash and its effects is an ongoing journey of discovery. As our tools and methods for observing the universe improve, so too will our understanding of the intricate processes that govern the evolution of stars. From the birth of a star to its explosive death, the helium flash remains a fascinating and crucial part of the cosmic story, one that will continue to captivate astronomers and stargazers for generations to come. In the end, the helium flash serves as a reminder that the universe is a place of constant change, where stars are born, evolve, and die in a never-ending cycle. It is a process that has been happening for billions of years and will continue for billions more. The mysteries of stellar evolution, including the helium flash, are part of a larger story, one that spans the vast expanse of space and time and touches every corner of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.